Namaste. In an earlier video, we used this 3D printed Earth to understand concepts like latitude and longitude. Can we use the same scheme to mark the position of the sun and stars in the sky? Not really. We will learn another way in which locations of these celestial objects are decided. Let us use the same sphere to represent Earth. We will insert this transparent disk in between these two hemispheres. This disk represents the equatorial plane, outward extension of the Earth's equator. While exploring the celestial sphere, we always consider Earth along its axis vertically, not like this, tilted on its axis with respect to its orbital plane. The sky has no shape. It extends infinitely outwards. Sun, moon, planets and stars are scattered through space at different and very large distances. However, if we assume that sky is a hollow sphere with Earth at its center and all other celestial bodies on its surface, then it becomes really easy to study motions and positions of the celestial bodies. This imaginary model is called celestial sphere. These large acrylic hemispheres together will represent our celestial sphere. This point here represents the celestial North Pole, while this one celestial South Pole. These points are the extensions of the poles we have on Earth. Line dividing the two hemispheres is the celestial equator. In this new setup, axis of both the sphere is the same. So are the poles. Let us attach this paper star here. Every day, we see stars rising in the east and setting in the west. It takes approximately 24 hours for a star to come to the same place. Let us place this star near the celestial North Pole. Any star near the pole is called pole star. Sky seems to rotate around it all night. Note that it is not exactly at the pole position, but slightly away from it. Its current name is Polaris, which is also known as Dhruvatara. Celestial sphere seems to be moving with all the stars in a clockwise direction. But it is not really the case. The stars themselves do not move on the celestial sphere and therefore have a unique location on it. In fact, it is the Earth which is moving in an anti-clockwise direction when seen from the top, all the way above from the celestial North Pole. However, our star Sun is an exception. It changes position in a periodic fashion during the year. The path it traverses on the celestial sphere is known as ecliptic. How about the path of the Sun on the celestial sphere? Is it along the equator or is it circular in nature? Not really. As we assume that Earth's axis is vertical in this setup, the orientation of Sun's path will change. Let me explain with the help of this small model. As you know, Earth revolves around the Sun with its axis tilted. Thin strip joining Sun and Earth represents the ecliptic plane. Now let us change the roles. Now the Sun is moving around the Earth. But in this setup, as the Earth's axis is vertical, Sun is changing its position up and down along its axis. Half part of the year, Sun is in the northern hemisphere, while for the remaining part, it is in the southern hemisphere. Only on two occasions, it is on the equatorial plane. These 2 days are known as equinoxes, as we know. Same can be represented on the celestial sphere with the help of this thin black ring. It represents the imaginary path the Sun travels along the celestial sphere throughout the year. This path is also known as ecliptic, literally path on which eclipses take place. Other planets also move along this ecliptic plane, but we will discuss this some other time. How do we identify the position of the Sun and the stars on the celestial sphere? Here on Earth, we had a prime meridian going through Greenwich as a reference point for longitude and equator as a reference point for latitude. There is no prime meridian in space. Conventionally, the point where the ecliptic and the equator crosses is considered as a reference or starting point while marking positions of the celestial bodies in east-west directions. But there are 2 points, one on this side and the other on this side. Which one should be taken? When the Sun crosses the equatorial plane and its direction is upward, it is taken as a reference point. It is also known as the first point of Aries. It was the case when this convention started. But now, due to phenomena known as precession, it has drifted from its position. Now, it is in the constellation of Pisces. Let us attach stars at various places on the sphere. There are 4 systems for measuring the location of the stars. Each of these systems is helpful in a particular context to locate a celestial body. Ecliptic system, right ascension and declination, that is equatorial system, azimuth and altitude, which is horizontal system, and hour angle and declination, which is a meridian system. We'll discuss the equatorial system in this video. Right ascension is the term used to indicate position of the star in the east or west directions from the origin, just like longitude on Earth. But there are a couple of differences. It is not measured in degrees, minutes and seconds though, just like longitude. It is measured in hours, minutes and seconds. And there is no east and west direction either. As you know, this is the reference point, intersection of the vernal equinox and celestial equator. Let us look at it from the top. This is the celestial North Pole. If we start from here in an anti-clockwise direction, that is from west to east in conventional terms, we will cover the full 360 degrees when we have arrived at this location again. I can divide this circle into 24 parts. Each part is 15 degrees. We don't have to use east or west directions or plus and minus signs to specify this part of the coordinates. Right ascension of this green star is 45 degrees. For the white star, it is 135 degrees. Yellow star is 255 degrees and pink star is 345 degrees. Instead of saying 15 degrees from the origin, I can also say that it is 1 hour from the origin. There are 24 divisions and each division corresponds to 1 hour. In earlier days, people used hours to tell the difference between two stars. For example, star A will rise 2 hours after star B. Instead of saying the distance between two stars is 30 degrees. With this context, right ascension for the white star is 6 hours. Now it is 12 hours. Now 18 hours and now 23 hours. Right ascension for this star is 2 hours and 30 minutes, or to be precise, 2 hours, 30 minutes and 10 seconds. 1 hour is divided into 60 minutes and each minute into 60 seconds. Angular separation between origin and green star is 15 degrees. Right ascension value for this star is 1 hour or 15 degrees. Angular separation between origin and yellow star is 30 degrees. Right ascension value is 2 hours for this star. How about this orange star? Angular separation is still 15 degrees, but on the other side. So right ascension for this orange star will be 360 minus 15 degrees, that is 345 degrees, which comes out to be 23 hours. For the brown star, it is 22 hours, as angular separation all the way is 330 degrees. Just like latitude, there is a similar term in this system as well, known as declination. It is the angular separation of the star from the celestial equator towards the poles. It is measured in degrees, minutes and seconds and not in hours, minutes and seconds like right ascension. All the stars we discussed are on the celestial equator. For them, declination will be 0 degree. Position of each star can be represented like this: 1 hour 0D, 2 hours 0D, 22 hours 0D, 23 hours 0D, like that. Our circle in astronomy is any great circle on the celestial sphere that passes through celestial poles. It is perpendicular to the celestial equator. The declination of celestial object is measured along its hour circle. This is 0 hour circle. This is 1 hour circle. This is 2 hour circle. This is 22 hour circle. How about black star? It is directly above the origin. It is on the 0 hour circle. Its right ascension is 0 hour. Its angular separation from the celestial equator is 15 degrees towards the celestial north pole. Its declination value will be plus 15 degrees. And this position can be represented as 0 hour and plus 15 degrees. For this yellow star, it will be 0 hour and plus 30 degrees. White star is in the celestial southern hemisphere. It's on the 0 hour circle and its declination value will be minus 15 degrees and the position will be 0 hour and minus 15 degrees. How about this orange star here? Right ascension for this star will be 22 hours and declination will be 30 degrees. You can also use this simulation from unl.edu to visualize how these coordinates change for a given star. As you can see, positions of the star are almost constant. Only exception for us is the Sun. In this simulation from javalab.org, we can see that declination and right ascension of the Sun changes throughout the year. At this location in April, it is 2 hours and 10 degrees, while at this location in June, it is 6 hours and 23 degrees. Its declination is 0 on two equinoxes and plus 23.5 degrees on summer solstice and negative 23.5 degree on winter solstice. You can use this simulation to know more about positions of the stars in different constellations as well. We'll discuss other coordinate systems in the next video. Thank you.